All right, welcome. So today we're going to take a look at the Cartesian equation of a line. So yesterday we looked at the parametric equation of a line in a plane or on a plane, and we looked at the vector equation of a line on a plane. So we learned that the parametric equation was just the x and y components. We just broke that up. And we looked at the vector equation, which sort of like put those pieces together to write the equation of a line. Remember that x and y is just the position of a vector of any point on the line, and x0, y0 is the position vector of a particular point on the line. AB was the direction vector for the line, and t is just some random scalar, which is an element of the real numbers. And t is just like our parameter that we're going to use to represent or to allow us to tell us any point on that particular vector line. And then we use the r as the notation to represent the vector joining the origin to the point at any particular point on that line. So today I want to tell you about the normal vector. So a normal vector is any vector that is perpendicular to a line. So that means that if we're given a vector u, the dot product between u and the normal vector will always be 0. So that's one of the properties that we learned in our last unit. So we're going to let the normal vector be represented by the letter n. That makes sense. And we're going to use the capital letter A and B for that, and you'll see why in just a little bit. So we're going to let that be the normal vector to the line that passes through, again, some random points. We're going to use P0 as that sort of initial value or that initial point, and PXY just being a random point on the line. So if we wanted to represent the vector that spanned between that P0 and P, I could go ahead and find that by just subtracting my coordinates. So P0 and then P is going to be x minus x0 and then y minus y0. So that's going to be the vector coordinates for that vector between those 2 points. If I wanted to find the dot product with that normal vector, so again, for that normal vector, we're going to use capital A and capital B to represent the coordinates of that normal vector. So then I'm going to take AB and I'm going to do the dot product between my x minus x0 and my y minus y0. And because those two vectors are perpendicular, they're equal to 0. So dot product says I can just take the x coordinate from one of the vectors and multiply it by the x coordinate of the other vector. So A times x minus x0 plus B times y minus y0, that's still going to equal to 0. And if I use the distributive property, right, just to multiply that through, I'm going to get AX minus AX0 plus BY minus BY0. That's going to still be equal to 0. And I'm just going to rearrange this so that I have my AX and my BY together, and then just my random AX0 minus BY0 equals 0. And so what I can do is I can represent this last part of my formula that I did there for my dot product, and I'm just going to let this be represented by C. So I'm going to let C equal that expression, so minus AX0 minus BY0. And so doing that then gives us the Cartesian equation of a line, which is sometimes called the scalar equation of a line. So the scalar equation of the line, or the Cartesian equation of the line, is AX plus BY plus C equals 0. And you'll notice that this looks very similar to our equation in standard position back from grade 9. Okay, so Cartesian or scalar equation is what you might hear it represented as. So let's just practice finding some normal vectors before we take a look at writing some equations of lines. If I wanted to find the normal vector to any of these lines below here, I need to remember that my direction vector is represented by the letter m. think slope, right? And if I have an equation in slope-intercept form, I can identify the direction vector by just representing the slope. So maybe I'm going to go slope first. So the slope of this line is 4, but really it's 4 over 1, right? Where 4 is the rise and 1 is the run. So if I wanted to represent this as a direction vector, I would write this as 1, 4. And so if I wanted to write a normal vector, my normal vector would be coming from the fact that I'm looking for a line that is perpendicular to this original line. So if my slope of my original line was 4 over 1, well then the slope of a line that is perpendicular to that would be 1 over 4, but I'm going to make it negative. So the negative reciprocal of that. And so doing that, it allows me to find that normal vector in this case would be 4 and then negative 1. Remember, you can put that negative either with the x part or the y part. It makes no difference. If I was given an equation of a line or equation of a vector, using our parametric equations, I can also use that to help us figure out what is that direction vector. Remember, the direction vector comes from the coefficients in front of the variable t. So my direction vector is negative 5, 2, which means that the slope of this line would have been 2 over negative 5. Now a slope that is perpendicular to that would be 5 over 2, which means my normal vector would be 2, 5. You might get to a point where you don't need to write out the slope using rise over run. You could go right from that direction vector to a normal vector, knowing that all you do is switch the positions of the numbers, and then if it's negative, you make both numbers positive. If it was both numbers are positive, you make one of those negative. And then the last one says, can you find a normal vector to a line that is perpendicular to the normal of the vector in equation form, r equals 1, 2 plus t minus 3, 4. So again, I'm going to represent my direction vector. So my direction vector is negative 3, 4, which means the slope of that line would have been 4 over negative 3. Now, the slope that is perpendicular to that line would have been 3 over 4, which means the normal vector to that line, r, would be 4, 3. Now, remember that I am looking for a line that is perpendicular to the normal of this vector, which means that I'm essentially looking for a normal vector that was the same as my original direction vector. So I could use my direction vector as my vector, that normal vector that is perpendicular to the normal vector of vector equation r. So I could use negative 3, 4, or I could use the opposite one, which would have been 3, negative 4. Okay, so it makes no difference. And if you don't want to call that m because that was the original negative 3, 4, you can call it whatever letter you want. You can call it vector v, right? You know, we're not going to call it n because n we've already used, and we're not going to call it m because m's already used. So we'll just give it some random letter to use. Okay, so let's continue. So if I want to determine the Cartesian or the scalar equation of a line that has a normal vector to negative 1, and it passes through the point 4, 7. Well, I know that the Cartesian equation of a line is ax plus by plus c is equal to 0, where ab is the normal vector, and the xy comes from my random point. So my random point that the line passes through. And c is just just a regular number, okay? So it's a constant. So if I know what my normal vector is and I know the point that it crosses through, then I can figure out what my c value is going to be. And that's important for us to figure out. So I'm going to do 2 times 4, and then my b is -1. So -1 times 7 plus c is equal to 0. So 8 minus 7 plus c is equal to 0, or 1 plus c is equal to 0. If I isolate for c, I'm going to subtract 1 from both sides, so c is equal to -1. So now I can write with confidence, therefore, the Cartesian equation of the vector or the line on the plane is going to be, I'm still going to keep my a and b as my normal vector coefficients, so 2x and then minus y, and I'm also going to plug in the value for c, in this case is -1, and that's going to be equal to 0. Okay, so can we take all of that information that we've learned over the last few days and apply it to some graphing? So if I have an equation in parametric form represented by x equals 5 minus 2t and y equals -3 plus 4t, I can rearrange this. I could have written this instead of xy, I could write this as r, right, to go in that vector equation. So I could say that this is going to be the point 5, -3, plus my random scalar t, and then times -2, 4, which is my normal vector. Okay, my direction vector. This is the direction vector. So if I wanted to sketch a picture of my direction vector, I would go over -2 and up to 4, and this would be my direction vector. Okay? So I know that my line goes to the point 5, -3. So over to 5, down to -3, it's going to go through that point. But it also runs parallel to my direction vector. So my direction vector really says that I'm going to go over to the left, and I'm going to go up 4. So I can go over 2, up 4, boom, right there's another point on that line. Over 2, up 4, there's another point on that line. So I can now connect these in a nice straight line, and there is that line on a plane. If I wanted to now take that information and find the Cartesian equation, we might want to consider our symmetric equation that we looked at briefly yesterday. So the symmetric equation says that I need to isolate for t. So I'm going to take my x minus 5, because that's going to equal -2t. Then I'm going to take my x minus 5 and divide that by -2. That's going to give me t all by itself. I'm going to do the same thing with the y part of that parametric equation. So y this time plus 3 is equal to 4t, and then I'm going to divide both sides by 4 to get t by itself. So what this says now is that the symmetric equation says that the t in for the x part should also equal the t for the y part. So x minus 5 divided by 2 is equal to y plus 3 divided by 4. And now I can use this to come up with my Cartesian equation. I'm going to do some cross multiplication here if you want to think about it like that. So 4 times x minus 5 is equal to -2 times y plus 3. So I'm just getting rid of those denominators from those fractions. And I'm going to apply the distributive property. So I get 4x minus 20 is equal to -2y minus 6. And I'm going to bring everything to one side. Might as well bring it over to the left-hand side. So 4x plus 2y minus 20 plus 6 is equal to 0. Simplify any like terms, in this case those two constants at the end. So I have 4x plus 2y minus 14 is equal to 0. I can keep my equation like this, or if I wanted to, I could say, look, all of these numbers are divisible by 2, so I could also write this as 2x plus y minus 7 is equal to 0. So try some questions from 8.2. So that's the textbook page that you're going to get. So try questions 1 to 12, and then you can skip 13 and try number 14. If you have any questions, please let me know. I will see you back at school tomorrow.